A heatsink is a passive heat exchanger that transfers the heat generated by an electronic or a mechanical device into a coolant fluid in motion. Then transferred heat leaves the device with the fluid in motion, therefore allowing the regulation of the device temperature at physically feasible levels. In computers, heat sinks are used to cool central processing units or graphics processors. Heat sinks are used with high-power semiconductor devices such as power transistors and optoelectronics such as lasers and light-emitting diodes, where the heat dissipation ability of the basic device is insufficient to moderate its temperature. A heat sink is designed to maximize its surface area in contact with the cooling medium surrounding it, such as the air velocity, choice of material, protrusion design and surface treatment are factors that affect the performance of a heat sink. Heat sink attachment methods and thermal interface materials also affect the die temperature of the integrated circuit. Heat transfer principle. A heat sink transfers thermal energy from a higher temperature device to a lower temperature fluid medium. The fluid medium is frequently air, but can also be water, refrigerants or oil. If the fluid medium is water, the heat sink is frequently called a cold plate. In thermodynamics, a heat sink is a heat reservoir that can absorb an arbitrary amount of heat without significantly changing temperature. Practical heat sinks for electronic devices must have a temperature higher than the surroundings to transfer heat by convection, radiation, and conduction. The power supplies of electronics are not 100% efficient, so extra heat is produced that may be detrimental to the function of the device. As such, a heat sink is included in the design to disperse heat to improve efficient energy use. To understand the principle of a heat sink, consider Fourier's law of heat conduction. Fourier's law of heat conduction, simplified to a one-dimensional form in the x direction, shows that when there is a temperature gradient in a body, heat will be transferred from the higher temperature region to the lower temperature region. The rate at which heat is transferred by conduction is proportional to the product of the temperature gradient and the cross-sectional area through which heat is transferred. Consider a heat sink in a duct, where air flows through the duct, as shown in Figure 2. It is assumed that the heat sink base is higher in temperature than the air. Applying the conservation of energy for steady-state conditions and Newton's law of cooling to the temperature node shown in Figure 2 gives the following set of equations, where using the mean air temperature as an assumption that is valid for relatively short heat sinks. When compact heat exchangers are calculated, the logarithmic mean air temperature is used. Is the air mass flow rate in kilogram per second. The above equations show that when the airflow through the heat sink decreases, this results in an increase in the average air temperature. This in turn increases the heat sink base temperature, and additionally, the thermal resistance of the heat sink will also increase. The net result is a higher heat sink base temperature. The increase in heat sink thermal resistance with decrease in flow rate will be shown later in this article. The inlet air temperature relates strongly with the heat sink base temperature. For example, if there is recirculation of air in a product, the inlet air temperature is not the ambient air temperature. The inlet air temperature of the heat sink is therefore higher, which also results in a higher heat sink base temperature. If there is no airflow around the heat sink, energy cannot be transferred. A heat sink is not a device with the magical ability to absorb heat like a sponge and send it off to a parallel universe. Natural convection requires free flow of air over the heat sink. If fins are not aligned vertically, or if fins are too close together to allow sufficient airflow between them, the efficiency of the heat sink will decline. Design factors. Thermal resistance for semiconductor devices used in a variety of consumer and industrial electronics. The idea of thermal resistance simplifies the selection of heat sinks. The heat flow between the semiconductor die and ambient air is modeled as a series of resistances to heat flow. There is a resistance from the die to the device case, from the case to the heat sink, and from the heat sink to the ambient air. The sum of these resistances is the total thermal resistance from the die to the ambient air. Thermal resistance is defined as temperature rise per unit of power, analogous to electrical resistance, and is expressed in units of degrees Celsius per watt. If the device dissipation in watts is known, and the total thermal resistance is calculated, the temperature rise of the die over the ambient air can be calculated. The idea of thermal resistance of a semiconductor heatsink is an approximation. It does not take into account non-uniform distribution of heat over a device or heatsink. It only models a system in thermal equilibrium, and does not take into account the change in temperatures with time, nor does it reflect the non-linearity of radiation and convection with respect to temperature rise. However, manufacturers tabulate typical values of thermal resistance for heatsinks and semiconductor devices, which allows selection of commercially manufactured heatsinks to be simplified. Commercial extruded aluminium heatsinks have a thermal resistance ranging from 0.4 degrees Celsius W for a large sink meant for TO3 devices, up to as high as 85 degrees Celsius W for a clip-on heatsink for a TO92 small plastic case. The popular 2N3055 power transistor in a TO3 case has an internal thermal resistance from junction to case of 1.52 degrees Celsius W. The contact between the device case and heatsink may have a thermal resistance of between 0.5 up to 1.7 degrees Celsius W, depending on the case size and use of grease or insulating mica washer material. The most common heatsink materials are aluminium alloys. Aluminium alloy 1050A has one of the highest thermal conductivity values at 229 W per meter K but is mechanically soft. Aluminium alloys 6061 and 6063 are commonly used, with thermal conductivity values of 166 and 201 W per meter K, respectively. The values depend on the temper of the alloy. Copper has excellent heat-sink properties in terms of its thermal conductivity, corrosion resistance, biofouling resistance, and antimicrobial resistance. Copper has around twice the thermal conductivity of aluminium and faster, more efficient heat absorption. Its main applications are in industrial facilities, power plants, solar thermal water systems, HVAC systems, gas water heaters, forced air heating and cooling systems, geothermal heating and cooling, and electronic systems. Copper is 3 times as dense and more expensive than aluminium. Copper heat sinks are machined and skived. Another method of manufacture is to solder the fins into the heat sink base. Aluminium heat sinks can be extruded, but the less ductile copper cannot. Diamond is another heat sink material, and its thermal conductivity of 2000 W per meter K exceeds copper 5-fold. In contrast to metals, where heat is conducted by delocalized electrons, lattice vibrations are responsible for diamond's very high thermal conductivity. For thermal management applications, the outstanding thermal conductivity and diffusivity of diamond is an essential. Nowadays, synthetic diamond is used as submounts for high-power integrated circuits and laser diodes. Composite materials can be used. Examples are a copper-tungsten pseudoalloy, AlSiC, dimalloy, and E-material. Such materials are often used as substrates for chips, as their thermal expansion coefficient can be matched to ceramics and semiconductors. Fin efficiency is one of the parameters which makes a higher thermal conductivity material important. A fin of a heatsink may be considered to be a flat plate with heat flowing in one end and being dissipated into the surrounding fluid as it travels. to the other. As heat flows through the fin, the combination of the thermal resistance of the heat sink impeding the flow and the heat loss due to convection, the temperature of the fin and, therefore, the heat transfer to the fluid, will decrease from the base to the end of the fin. Fin efficiency is defined as the actual heat transferred by the fin, divided by the heat transfer were the fin to be isothermal. Equations 6 and 7 are applicable for straight fins, where HF is the convection coefficient of the fin air, 10 to 100 with water, 500 to 10,000 with K is the thermal conductivity of the fin material aluminium, 120 to 240 with LF is the fin height, TF is the fin thickness. Fin efficiency is increased by decreasing the fin aspect ratio, or by using more conductive material. Spreading resistance, another parameter that concerns the thermal conductivity of the heat sink material, is spreading resistance. Spreading resistance occurs when thermal energy is transferred from a small area to a larger area in a substance with finite thermal conductivity. In a heat sink, this means that heat does not distribute uniformly through the heat sink base. The spreading resistance phenomenon is shown by how the heat travels from the heat source location and causes a large temperature gradient between the heat source and the edges of the heat sink. This means that some fins are at a lower temperature than if the heat source were uniform across the base of the heat sink. This non-uniformity increases the heat sink's effective thermal resistance. To decrease the spreading resistance in the base of a heat sink, increase the base thickness. Choose a different material with better thermal conductivity. Use a vapor chamber or heat pipe in the heat sink base. Optimization. The shape of fins must be optimized to maximize heat transfer density and to minimize the pressure drop in the coolant fluid across the heat sink where the space and the materials used for the fin surfaces are constraints. Many shapes exist in the literature, ranging from elliptical and cylindrical cylinders, conical shapes to more sharpened surfaces such as rhombus, square sections. Fin arrangements. A pin fin heatsink is a heatsink that has pins that extend from its base. The pins can be cylindrical, elliptical or square. A pin is by far one of the more common heatsink types available on the market. A second type of heatsink fin arrangement is the straight fin. These run the entire length of the heatsink. A variation on the straight fin heatsink is a crosscut heatsink. A straight fin heatsink is cut at regular intervals. In general, the more surface area a heatsink has, the better it works. However, this is not always true. The concept of a pin-fin heatsink is to try to pack as much surface area into a given volume as possible. As well, it works well in any orientation. Cordy-Bang has compared the performance of a pin-fin and a straight-fin heatsink of similar dimensions. Although the pin-fin has 194 square centimeters surface area while the straight-fin has 58 square centimeters. The temperature difference between the heatsink base and the ambient air for the pin-fin is 50 degrees Celsius. For the straight fin it was 44 degrees Celsius or 6 degrees Celsius better than the pin-fin. Pin-fin heatsink performance is significantly better than straight fins when used in their intended application where the fluid flows axially along the pins rather than only tangentially across the pins. Another configuration is the flared fin heatsink. Its fins are not parallel to each other, as shown in Figure 5. Flaring the fins decreases flow resistance and makes more air go through the heatsink fin channel, otherwise, more air would bypass the fins. Slanting them keeps the overall dimensions the same, but offers longer fins. Forgan, al. have published data on tests conducted on pin-fin, straight-fin and flared-fin heatsinks. They found that for low approach air velocity, typically around 1 meter per second, the thermal performance is at least 20% better than straight-fin heatsinks. Lazance and Egink also found that for the bypass configurations that they tested, the flared heatsink performed better than the other heatsinks tested. High conductivity materials in the recent years. Utilization of high conductivity materials have been proposed for electronic cooling and for enhancing the heat removal from small chips to a heat sink, because the space occupied by high conductivity materials together with the cost of the two elements of major concern. Cavities embedded in a heat source are the regions formed between adjacent fins that stand for the essential promoters of nucleate boiling, or condensation. These cavities are usually utilized to extract heat from a variety of heat-generating bodies to a heat sink. Conductive thick plate between the heat source and the heat sink. Placing a conductive thick plate as a heat transfer interface between a heat source and a cold flowing fluid may improve the cooling performance. In such arrangement, the heat source is cooled under the thick plate instead of being cooled in direct contact with the cooling fluid. It is shown that the thick plate can significantly improve the heat transfer between the heat source and the cooling fluid by way of conducting the heat current in an optimal manner. The two most attractive advantages of this method are that no additional pumping power and no extra heat transfer surface area. That is quite different from fins. Surface color. The heat transfer from the heat sink occurs by convection of the surrounding air, conduction through the air, and radiation. Heat transfer by radiation is a function of both the heat sink temperature and the temperature of the surroundings that the heat sink is optically coupled with. When both of these temperatures are on the order of 0 degrees Celsius to 100 degrees Celsius, the contribution of radiation compared to convection is generally small, and this factor is often neglected. In this case, finned heat sinks operating in either natural convection or forced flow will not be affected significantly by surface emissivity. In situations where convection is low, such as a flat non-fin panel with low airflow, radiative cooling can be a significant factor. Here the surface properties may be an important design factor. Matte black surfaces will radiate much more efficiently than shiny bare metal. A shiny metal surface has low emissivity. The emissivity of a material is tremendously frequency dependent, and is related to absorptivity. For most materials, the emissivity in the visible spectrum is similar to the emissivity in the infrared spectrum. However, there are exceptions, notably certain metal oxides that are used as selective surfaces. In a vacuum or in outer space, there is no convective heat transfer. Thus, in these environments, radiation is the only factor governing heat flow between the heat sink and the environment. For a satellite in space, a 100 degrees Celsius surface facing the sun will absorb a lot of radiant heat, because the sun's surface temperature is nearly 6000 Kelvin, whereas the same surface facing deep space will radiate a lot of heat, since deep space has an effective temperature of only a few Kelvin.